Hi everybody, welcome to the 2221/2121 seminar, to the first part. Here we'll be covering the first two topics. I'll be here covering the first major section, which is linear ODEs, and later today, Oscar is going to cover dynamical systems. So let's just get started with linear ODEs. So we start with this thing called a linear differential operator. It's just a way of writing out every linear differential equation, or at least the left-hand side of it, which is usually it's just like a coefficient with the mth derivative attached to it, and then we add this up with every derivative. And that's what this sigma sum is meant to represent, where this represents the jth derivative of u. And so, yeah, what I wrote is basically this line over here. It's just the sum of a coefficient in terms of x times by the mth derivative of u, and then the m minus 1th coefficient, which is also in terms of x, times the m minus 1th derivative, and so on. And ODE, we call it singular if the leading coefficient goes to 0. The intuition behind this is if you have something like this equation, usually our goal is to make the highest degree term the subject. And if you try to do that here, so move the u over and then make u dash the subject, the issue here is sometimes you're dividing by 0, and that means this is singular. And when an ODE is non-singular, we'll show that there are some nice properties of the ODE. Okay, a homogeneous ODE is when the right-hand side of it is 0. So the differential stuff on the left-hand side equals to 0. Yeah. So for example, this. But it's inhomogeneous if the right-hand side is not 0. So it's this. And this one, I'll be calling it the forced term. You might hear like forcing term, forcing function, or something similar. Yeah, so for example, the same differential equation but with cos on the right-hand side, this is inhomogeneous. Okay, now let's solve this homogeneous linear ODE. So this one's a basic one. Just think of this as you want to write out the characteristic polynomial. Which is, imagine just turning like the second derivative to a power of 2. What you'll get is r squared plus r minus 1 equals 0. And then we want to solve this. So this gives us the solutions. Okay, so first you factorize it. Oh no, you have to solve it with quadratic formula. Minus 1 plus minus root 5 over 2. These are our two roots. Therefore, we have two solutions. We have u1, which is e to the, let's take one of the roots. Let's take the positive version of t, of x, if I'm using x here. And u2 of x is e to the other root. Yeah, and these are our two solutions. And in fact, we can combine these. We can make a general solution. Because if we take a linear combination of homogeneous solutions, we get another homogeneous solution. So we get some constant times this first one plus another constant times the second one. Yep, so it should look like this. Yeah, and so that's what this is doing. They used A and B instead of C1 and C2. Either way is fine. Now, in this general solution, there's constants attached, which are, they're not ideal, right? Because sometimes we want the exact equation, and the times that an exact equation arrives is when we have something called an initial value problem, which is the same thing as before, except they also attach these values to it, which is at each derivative, they give you what the output should be at a certain input. So for example, if we got this equation, the solution would be like, it'd be a e to the minus x. And then using this initial value, we can solve for this, this value of a. Okay, so here's some theorems. If f is continuous and non-singular, so remember that means that the leading coefficient is never 0 over this interval, then the initial value problem has a unique solution. Right, so this is obviously very nice. And secondly, if L is a linear nth order differential operator and non-singular, then the set of all solutions to the homogeneous equation forms a kind of vector space of dimension m. Really, what that's saying is when you solve an nth order differential equation, usually you're going to get m different solutions, as in u1x, u2x, u3x, all the way up to umx, right? These will all be different solutions. And then if you take a linear combination of these, then you'll get the general solution for that ODE. Okay, so here's an example of an initial value problem. Let's solve this, given that u0 is something, u-0 is something else. So recall from before, our solution was u of x equals to c1 e to the 1 minus 1 plus root 5 over 2 of x plus c2 e to the minus 1 minus root 5 over 2 x. And now we can sub in some values. First, I'll find the derivative. This will be c1 times that plus c2 times that coefficient again. Okay, and then we get our two equations from the initial values. U of 0, in this expression it's c1 plus c2 because the power goes to 0. I don't know why I changed to t halfway through. C1 plus C2, that's meant to equal to 0. And U dash of 0 is C1 of negative 1 plus root 5 over 2 plus C2 of negative 1 minus root 5 on 2. Because again, the power goes to 0. And now this should equal 2. And if you solve these, so just solve, if you just solve, if I can draw a box, that would be great. If you can just solve these two equations, you should get the solutions. Well, actually, we'll see on the next slide what we get. Yeah, so they did the same thing, but they called it A and B instead. And they found that A was 2 over root 5, and B is negative 2 over root 5. Okay, cool. So solving IVPs is just solving as you normally would, and then plugging in values to figure out what the constants are. Okay, linear independence. We say that m functions are linearly independent on this interval if this equation holds, as in a linear combination. If we have a linear combination of these functions and it equals to 0, then each of the coefficients has to be 0. In other words, the only way this is true is if it's 0 u1 plus 0 u2 all the way up to 0 And linear independence is, or it's basically saying that all of these functions are very different in some way. Okay, another definition. Yeah, so unfortunately this this part of the course is quite formula heavy. Oh, there's a lot of definitions that you just need to remember. There's a thing called a Wronskian, which, okay, this definition, it's just saying that if you're in row I, column J, you're taking the I minus 1 derivative of the jth entry. But it's probably just easier to look at it like this. In the first column you have all the ones, and then you take the derivative as you go down. And then second column you have the 2's, third column you have the 3's. Of course, this is just in the 3x3 case. You can define it for any other square matrix. Or, sorry, for any other number of functions. Okay, so this might seem a bit random, but it does have some nice properties. And those nice properties are worth how kind of random this seems. So there's a relationship with linear independence. If we have a non-singular linear homogeneous mth order ODE, so just non-singular LU equals 0 or over AB, then either the Wronskian 0 and the solutions are linearly dependent, so that means they're not linearly independent, or it's not 0 and they are linearly independent. Okay, so what we're seeking is for a non-zero determinant. Yeah, so a good way to remember this, it might be related, it might not be, I haven't thought too much about this, but if the determinant's not 0, that implies like invertibility, which is just a nice property to have, and this is also a nice property to have. Okay, some extra lemmas. First lemma is, if these are linearly dependent over the interval, then the sorry, just had some issues there. So yeah, as I was saying, the Wronskian of this differential equation will satisfy this equation. The proof for this, I think the proof is very annoying for higher degree differential equations, just because the Wronskian is going to look very ugly. But this equation, normally used for like usually second order or maybe even third order, it just holds. Okay. We want to show that the homogeneous solutions to this ODE are linearly independent. So yeah, we're going to solve it, and then we're going to use the Wronskian to determine if they are linearly independent. So the characteristic equation, I'll just call it the CE, is r squared plus 3 equals to 0. And this gives us the solutions plus minus root 3i. And you should know that this means our homogeneous solutions are going to be a cos root 3x and b sine root 3, negative, yes, positive root 3x. That would be the same thing anyway if it was positive or negative. And that means if we were to compute the Wronskian, and a good thing to remember is the Wronskian's a function, it's just a function in terms of x. So it's going to look like this. We'll see on next slide how they calculate it. Yeah, so they did it in terms of t instead, which is fine. They got these same solutions. They take the determinant of this Wronskian, which is u1, u1 dash, u2, u2 dash. You end up getting root 3, which is not 0. which means that the homogeneous solutions are linearly independent, going back to this slide over here. Okay, yep, so that question's done. Next question here. Prove that if U1 and U2 are solutions of this differential equation, then the Wronskian satisfies this. So this is just asking you to prove, where was it? It's asking you to prove this identity for the for a specific case where it's, I believe, second order. Right, okay. So the way we're going to start this off, we want to find the Wronskian, right? That's the only way we're going to be able to do this. And yeah, so the Wronskian being the determinant of this matrix. Well, good thing we know what the determinant of 2 by 2 matrix is. It's this main diagonal, U1, U2 dash, minus the product of the not so main diagonal. You get this. And then you also want to find the derivative of this term. Right, so therefore W dash equals to, and here at this point it's just using a bunch of product rule. It's a bit tedious, so I won't go through it, but I'm sure you're able to use product rule there. And then you're going to have a bunch of terms, and the way you're going to simplify it is you're going to notice since U1 and U2 are solutions, they're going to satisfy A2 U1 double dash plus A1 U1 dash plus A0 U1 equals to 0, and the same thing with 1 and the same thing with 2. So let's just look at what they did. So yeah, as I said, this is just from the actual differential equation. U1 and U2 are solutions, so we get these two equations. And then we compute W and its derivative. It's tedious, but we know it probably should work. And then we're going to compute what they wanted to compute, which is this term, which is A2 of W dash plus A1 of W. This is just copying the values from above. And at this point, we want to simplify it. Yeah, we're going to factorize it into, or we're trying to make it look like, 1 and 2. Right, we want to make something that looks like these equations. And what they do is they get like the first section of this equation. And so by rearranging, if you move this over to the other side, you get equals to negative A0 U1, and same thing here. And so they can replace these values with these values. And that's what they do here. And then they get two of the same thing, except one's negative, and it turns out to be 0. So yeah, this is just tedious work. It's one of those questions where you have to just do it. There's no good way around it. Okay, and then what was part C? Part C was determine the form of W when U1 and U2 are solutions of this equation. Okay, the idea here is we don't want to solve this equation, obviously. So instead what we're going to do is we're going to find the Wronskian, or at least the differential equation that represents the Wronskian, which will be 1 minus x squared W dash plus or minus 2xw equals to 0. And then we should be able to solve this. So yeah, we have this equation that I just wrote. We can solve this using integrating factor. So first we change this into so that the leading coefficient is 1. So divide by the leading coefficient. Yep, so you get this. And then using integrating factor, the integrating factor is e to the integral of this middle term, or this second coefficient. If you do the integral, not a particularly hard one, you'll get 1 minus x squared. And yeah, so that gives you the left-hand side here is the derivative of 1 minus x squared. Oh, sorry. If you multiply this by integrating factor, it turns out you actually just get back to the original equation. But the left-hand side here now can be written as the product rule, d over dx, 1 minus x squared w equals to 0. And now we can solve for w. What you'll get for w is, well, that means the inside of the derivative is just a constant, and then divide the constant over, you get w is c over 1 minus x squared. Okay, here's another formula you have to remember. Reduction of order. So let's say we have a second order ODE in this form, and we know one of the solutions. Then the second solution is given by this equation. Not much to say here. I mean, I guess you can see the derivation of this probably involves integrating factor, since it has the integral of this coefficient dx. But it's not that important to know how to derive it. It's just important that you have the formula, unfortunately. So, okay, show that u1 e to the 2x is a solution to this, and then find the general solution using reduction of order. So the idea here is we have one of the solutions, and then we're going to use it to find u2. Okay, so checking that e to the 2x is a solution is pretty straightforward. I'll start from the left-hand side. The left-hand side will be x plus 2. If you diff this twice, a 2 will come out twice, so you'll get 4 e to the 2x. And then minus 2x plus 5 u dash. U dash is just 2 e to the 2x. And then plus 2 of u, which is e to the 2x. And then hopefully what happens is the coefficients become 0. Or like if you group them up, they go 0. So I'll take out the x, 4x e to the 2x. And the constant term is 8 e to the 2x. And then we have minus 4x e to the 2x, minus 10 e to the 2x, plus 2 e to the 2x. And you should be able to see the x e to the 2x cancels out. Everything else also cancels out, and we get 0. Hence, find the general solution using the reduction of order method. So we're just going to use this equation here. Okay, so u2 is going to be u1 integral of dx over u1 squared integral, e to the integral of p of x. What should p of x be? Oh, okay, so I've done a small mistake here, which is this needs to have a leading coefficient of 1. So what we need to do in this case is actually rewrite it. So that the leading coefficient is 1. So like that. And now p of x is this term over here. Right. And at this point, it's just a matter of if you can integrate. So let's see what they did. Yeah, so this is for showing that it's a solution, which works. And then here we get this integral. As I said, p is equal to this weird fraction here. And the integral of p of x is minus 2x minus ln x plus 2. So now that goes into the power here. Okay, so this goes into there. u2 equals u1 integral of 1 over u1 squared e to the thing that we just found. And then I'm going to replace u1 with e to the 2x because that's what it is. You get e to the 2x here, e to the 4x here, everything else is the same. It simplifies to this integral, which you can do by parts. Once you use by parts, you'll get this result, which simplifies to negative 2x plus 5 over 4. Okay. Now, we're going to talk about how to guess for inhomogeneous linear or differential equations. Because sometimes, as we said before, you won't get equals to 0, you get equals to f. And in this case, the best thing to do is, if f is of a recognizable form, usually we can make a good guess about what it should be. Okay, so for example, don't worry about this too much. I guess we should worry about it a little bit because we need p of 0 to not be 0. So L equals P of D just means, so a polynomial in terms of D would be something like, what, D squared minus D plus 1, right? And that just means we're applying this to U. Okay, of order n with constant coefficients, assume that P of 0 is not 0. Then we can guess, if the right-hand side is a polynomial, up to degree x to the r, then that means our guess should also be a polynomial of that same degree. I probably shouldn't have used p of x here. I'm going to call it q of x. Yep, so if our ODE is of the form right-hand side equals to a polynomial with degree r, then we should guess a degree r polynomial. Okay, and an edge case that we always kind of need to check for is this only works if it's not already a homogeneous solution. Because obviously if it's a homogeneous solution, then the right hand side will be 0 instead of the q of x. Another guess we can make is, okay, again, if L is a polynomial of the differential operator, and P of mu is not 0, and here mu is the power of E, then if the right hand side, then this is a particular solution to the differential equation with e to the mu x on the right hand side. This P of mu you don't need to worry too much about. It is the same P as this, but all you need to remember is that this is a constant. It's just some constant. And that means that a particular solution of LU equals e to the mu x is just a constant times e to the mu x, right? That's what this is. And again, if it's not already a homogeneous solution. If it is, then usually we just add a power of x, add an x in front of it. So if e to the mu x is already taken, then we go into x e to the mu x. If that's already taken, then we pick x squared e to the mu x. Okay, so find the unique solution to this ODE. Okay, so there's two parts to this. We need to find the homogeneous solution, and then we need to find the particular solution. And actually in this case it's a step 3 since it's an initial value problem. The general solution is UH plus UP, and then sub in the initial value problem values. So these are our 3 steps. Wow. So firstly, the homogeneous version of this equation is this. The characteristic equation is r squared plus 4r plus 3 equals to 0, which gives you the solutions -1 and -3 if you solve it. Okay, and that means that our UH is going to be, remember the two solutions we get out of this are e to the minus x and e to the minus 3x, and then we just put constants in front, and this is our general homogeneous solution. For inhomogeneous solution, since this is a degree 2 polynomial, our guess is UP equals to ax squared plus bx plus c. So it's just another degree 2 polynomial. And at this point, it's pretty tedious. You plug this into the left-hand side, and then set it equal to the right-hand side. And okay, this should be on the next slide. I'll just let the next slide do it for me. So as we said, this is the homogeneous solution. So the fourth term, remember it's the thing on the right-hand side, is a poly of degree 2. And yeah, we also should have checked that p of 0 equals to is not equal to 0. And here, this p is the characteristic equation. Right? That's just what the characteristic equation is defined as. It's the differential polynomial on the left, if that makes sense. Okay, and also our homogeneous solution didn't contain a polynomial, so we're allowed to guess this. So we find its two derivatives, and then we plug it into the left-hand side of the equation. We get this expression, which is meant to equal to 9x squared, and then if you equate the coefficients, you find a is 3, b is negative 8, c is 26 on 3. So again, not hard, just a bit tedious. So this gives us UP equals to 3x squared minus 8x plus 26 on 3. So our general solution, which is a homogeneous part plus the particular part, is, well, the homogeneous part plus the plus the particular part. And now we're going to use the initial conditions. So we find its derivative, which is this expression, and then if we sub in 0 into the original and its derivative, then we'll get these expressions, which again you can solve. It's fairly straightforward, it's just a bit tedious. Solve for C1 and C2 simultaneously. We get these two values, and those are the coefficients of e to the minus x and e to the minus 3x. And this is our final solution. Okay, here's another question. Let p of z be z minus 1, z plus 2 squared, z squared plus 1. And d is just the differentiation operator. Write down the general solution of the fifth order linear homogeneous ODE PD of VU. So this is again our characteristic equation. That's what the job of this is. And that means the roots are going to be z is equal to 1, -2, -2, I, and minus I. So I'm just looking at the roots of this. And that means our general solution is going to be, okay, I'm going to need a bunch of constants. Okay, but for each of these, for the 1, I get e to the x. For -2, I get e to the minus 2x. For a -2 again, remember e to the minus 2x is already taken, so I just put an x in front. And then when I have I and minus I, that turns into cos and sine. Okay, so that's what this is. And then part 2 is find a particular solution, or at least the form of it, to the inhomogeneous ODE with this on the right hand side. So the answer here is it's a bit crazy, but I'll break it down for you. This is not meant to be a 2. This is meant to be, oh, I guess it didn't fit. It's meant to be ax squared e to the minus 2x. Okay, so here's where everything came from. We can split this into 3 sections. Into this section, and this really big section. On the right-hand side, we have also 3 bits. So the forcing term has 3 parts to it. It has this term, and this term. For exponential, what we wanted to guess was e to the minus 2x. But e to the minus 2x is taken, so we're going to consider x, e to the minus 2x. But that's also taken, that's also taken, so we guess x squared. That's where the first term comes from. It's ax squared e to the minus 2x. Okay, so we've dealt with that. The second term is a polynomial. It's a degree 2 polynomial, which means we guess another degree 2 polynomial, which is this part. And then for the cos x, this part's really annoying, and I don't think we mentioned this, but if we have a polynomial times a trig function, let's say it was something like this. I should again use a different letter here, not p. Then my guess is r of x cos x plus s of x sin x, where these 2 polynomials have the same degree as q of x. Yeah, so in this case, since this is a degree 2 thing in front of a cos, I have a quadratic in front of cos and a quadratic in front of sine. Okay, and then what's up with this x here? Okay, so the reason why we need the x there is because in our polynomial, we're going to have a regular cos x term somewhere. Like if you think about the constant term of the rx polynomial, it's going to be r0, and then with the cos x here, it's going to be this. But this is already part of our inhomogeneous solution. We already have a cos x and a sin x, and what that means is we need to put these 2 x's here to account for that. So similar to how we did for e to the x. Okay, now there's a really cool named method, a method of annihilators. If we have a inhomogeneous differential equation, and we can find a differential operator that annihilates f of x, which means if we can find a way to, like a way to diff this that makes it 0, if that makes sense, then we can apply it to both sides and end up with a homogeneous differential equation. So an example, they gave us an example. If the right-hand side was x squared, then if we apply d3 to it, d3 will annihilate it. So because if you diff this 3 times, it goes to 0. Another example is if you have e to the x on the right-hand side, and you apply d minus 1 to it, d minus 1 annihilates e to the x. Because if you diff it and then subtract it from the original, you get 0. So if you apply that to both sides, then you get a homogeneous differential equation, and the solution to this will be a particular solution, right? That just works. So we're going to find a particular solution to this ODE. Okay, the solution's shown, but that's okay. The idea is I want to find an annihilator, so a combination of like derivatives that annihilate the right hand side. Since e to the x, as I mentioned before, is annihilated by d minus 1, and sine of x, you should know that if you diff this twice, then it will just become negative of the original. So d squared plus 1 is going to annihilate sine x. So the annihilator, d minus 1 d squared plus 1 is going to annihilate the entire right-hand side, because both of these terms are going to be annihilated. So we apply the annihilator to both sides. We get the annihilator times the characteristic polynomial for the left-hand side with the differential operator plugged in, times y of x, of y of x is equal to 0. Okay, and since AD PD is, okay, AD was d minus 1 d squared plus 1, and PD, if you look at the left-hand side, this is the same thing as d minus 1 squared of y. So it's going to be d minus 1 cubed here. The solutions to this are going to be e to the x e to the x squared e to the x because of the cube. And then from d squared plus 1, the solutions are plus minus I, right? So that gives us sine and cos. Chuck coefficients in front and we're happy. Okay, now something we can do here is, since in the original solution, if we were to solve just this thing equals to 0, it would give us e to the x and x e to the x. So that means these two terms in the particular equation don't really do anything, because when you plug it in, it's going to become 0 anyway. It's not going to contribute to e to the x plus sine x. So we can essentially ignore them. So that's what they did. They discard the first two terms because they're already in the homogeneous solution. And now using this function, we find the derivative, the second derivative, and we have to plug it into the original ODE. It's really tedious. You plug it into here, but it will cancel out into a nice equation. One thing you can note here is, to make your life a bit easier, you don't need to keep track of all the x squared e to the x terms, or all of the x e to the x terms, because you know they're all going to have to be 0 anyway. Because like, since it equals to e to the x plus sine x, then the x e to the x and the x squared e to the x terms obviously have to be 0. So that just saves a bit of time when you're doing the actual exam. But you'll get this expression, and that by matching coefficients, you get C3 is equal to 1/2, C4 will be 0, C5 will be 1/2. And we get a particular solution here. Okay, variation of parameters. From here, it's like strategies to find the particular solution after we found homogeneous solutions. That's what this section has like recently been about, as in like for the past few pages, past few slides. What we're saying here is, if I have two solutions, U1 and U2, then our actual solution is going to be, it's kind of like a pseudo linear combination. Like ideally, the best case is like something like this. Or that's just like a nice thing we can have. But then it's called variation of parameters, and what that means is, instead of having constant parameters, they turn into something variable. Right, so the coefficients become functions. And it turns out that this actually does yield a solution. If you plug this into the differential equation, you'll find that if this holds and this holds, then this will be a particular solution of the equation. Again, just another formula to memorize. Okay, variation of parameters to solve this. So remember the steps here. The first step is to solve the homogeneous case. And then step 2 is find v1 dash and v2 dash. And then 3 is, our solution is v1, so integrate this times u1 plus v2, which is the integral of this, times u2. Okay, so the homogeneous equation, I'm sure this slide says something about it. Yeah, so we have characteristic equation t squared minus 3t plus 2 is 0, which gives us the roots of this, well, the roots of this are going to be t equals to 1 and t is equal to 2, giving us these two homogeneous solutions. Since we want to use this formula, we need the Wronskian as well. So that's why the Wronskian is so important. The Wronskian is the determinant of u, u dash, oh sorry, u1, u1 dash, u2, u2 dash, and it turns out to be e to the 3x. And then we can plug in the things that we know. So this is the f of x, and we have our two solutions. So just remember our formula is v1 dash is negative y2 f of x over the Wronskian, and v2 dash is, that should not be y squared, that should be y1, oh sorry, y2. And this is y1 f of x over the Wronskian. Yeah, so you just plug those values in and you find these. And then we want to integrate to find v1 and v2. If you integrate negative sign, you get cos. If you integrate this by parts, you'll get this. And then the particular solution is v1 u1 plus v2 u2, which simplifies down to this. Okay, and now we can look at power series. So consider this second order linear homogeneous ODE. So we have this equation, or we can divide it by the leading coefficient to get this, where P of x is A1 divided by A2, and Q of x is A0 divided by A2. So we're going to assume that all of these are analytic at 0, which means they have power series, or convergent power series, and that it's not singular. So the leading coefficient is never 0. Remember, that means we can divide it without any issues. Then we can we have a solution that works in the radius of convergence of the three power series of A0, A1, and A2. And the solution will just be another power series. Oh wait, okay, that's not actually what this is saying. This is just saying that if P and Q are convergent in here, that's what this slide says, then what's happening here is, then we can guess a UZ as a power series, which will have a radius of convergence equal to that of P of Z and Q of Z. So essentially, guess U of Z equals a sum of AK Z to the K. Okay, yeah, and what that's saying is we're guaranteed a solution of this form and that it does converge. So you don't need to worry about checking that yourself. So here's an example. We want to find the solution to this, for which u0 is 0, u dash 0 is 6, so this is an initial value problem. We're going to rewrite this as u double dash minus z over, oh actually no, we won't do that. Yeah, it actually doesn't matter if you want to rewrite it like this or not. All that matters is that the leading coefficient is just not 0. Now this part of the course is extremely tedious. You need to plug this u and its derivatives into the original differential equation. So what will happen is you'll have 1 plus z squared of u double dash minus z of u dash minus 3 of u. So that was just the left hand side of the differential equation. Expanding the 1 out gives you this term. Expanding the z squared in gives you this term. So as you can see, it's k minus 2 versus a power of k. Minus, and then put the z in, you get z to the k inside, and then minus the sum of 3ak z to the k. That's just putting the 3 inside. At this point, our end goal is to have, wait, what is our end goal? Okay, let's just continue this for now. I just split up these terms, and I also noticed that the k equals to 1 and k equals to 0 terms of this are just 0, if you just check with the inside. So I can change it to start from 0. Same thing here, when k is 0, the inside 0, so I can add the 0 case. And the point of this is I want a big sum from 0 to infinity. Like this would just be nice to have. So if I combine the last 3 sums, since they all start from 0 now, I get k minus 1. Okay, so this is the first integral, and then this is the combination of the last 3 sums, which is k squared minus k minus 3. There should have been a 3 there, that's my bad. Okay, and now we can reindex the first sum. The point is, if you sub in 2 into here, it's going to start from z to the 0 anyway. And we want it to start from k is equal to 0. So what we do is we replace every k with c with a k plus 2. So k minus 1 becomes k plus 1, this becomes k plus 2, and the lower bound is now k plus 2 equals to 2, which means k is equal to 0. And then we combine the 2 sums and you get this. Finally, since this needs to equal to 0, then I need the coefficient to be 0. K is not going to be negative 1. So if I set this to be 0, I can just get rid of the k plus 1s for each power. And then for each power of k, I need this to be 0, which if you rearrange for a k plus 2, gives you this expression. Okay, and then at this point, we already kind of have a general solution, right? We have, depending on what A0 and A1 are equal to, then using this recursion, we can always jump 2 terms ahead. So this one will give us all the even terms. This will give us all the odd terms. And the way we find out what A0 and A1 are is we use the initial values. So U0 was equal to 0. A0 is equal to 0, which means if you use the recursion, all of the even terms are 0. Whereas A1 is equal to 6. And then you can calculate A3. But something to notice is that when k is equal to 3, this goes to 0. Meaning that A5, it'll be equal to, if you just look here, A5, if we plug in k is equal to 3, you'll get 0. And then again, using the recursion, every 2 terms after that is going to be 0. In other words, A1 is 6, A3 is 4, and then don't use this notation, but every odd term, I'll be rigorous here, A2k plus 1 is going to be 0, where k is an integer greater than or equal to, what is it? Integer greater than or equal to 2. And A2k equals to 0 for integers greater than or equal to 0, which gives us this solution. Okay, a Cauchy-Euler ODE is of this form. This is another standard form of a differential equation, and our guess in this case is x to the r, because if you plug in x to the r, you end up with a solution as long as r satisfies this equation, and it's called the indicial equation. So you can plug in x to the r in here and see for yourself. Okay, so if there are 2 solutions, then we guess a linear combination of them. But if there's if it's like a double root, then what you'll do is you'll take this, and then instead of putting an x in front of this as the second one, you put a log x in front. So remember how e to the x, we had to turn it into x e to the x? Think of it as the log version of this, which is x turns into log x times x. So we're going to find the solution to this ODE. So annoyingly, for the particular solution, I'm just looking a bit ahead here, this forcing term, we don't have a nice guess for it, so we're going to have to use variation of parameters for it. But that's not really the focus of this question. The focus is solving the Cauchy-Euler ODE. So we want the indicial equation. A is 2, B is 7, C is 3. Those are the coefficients. Which means the indicial equation is 2, 7, 3 in this equation. Solving the polynomial just gives us these two roots, which means our two homogeneous solutions are these. And then to find a particular solution, we just have to go through some tedious work. Recall the formulas for variation of parameters. And eventually we're ending up with u is v1 u1 plus v2 u2. Using the two solutions from before, I'm going to compute the Wronskian. So this is u1, this is u1 dash, this is u2, this is u2 dash. Find the determinant and you get this. And then plug those into v1 dash and v2 dash. Right, so remember for variation of parameters, we actually want the leading coefficient to be 1. So we're rewriting it with leading coefficient 1. And then v1 dash is the inside of this, so v1 would be the integral of negative y2 f of x over w of x. At this point, you just plug in your values and integrate. There's no good way around it. And you'll end up with this for v1. If you do the same thing for v2, then you'll get this. And so the variation of parameters leads to this solution, which if you simplify it, gives you this. Thus, our general solution is the homogeneous part plus this particular solution. Yeah, so unfortunately, there's not really much to explain here. It's just really tedious, and it's kind of just it's a just do it type of question where if you know the formula, you know it and you do it. Otherwise, you're a bit screwed. Okay, Frobenius normal form is a special case of an ODE. It's like a variation of Cauchy, was it Cauchy-Euler or the Euler-Cauchy? I don't remember. But it's a variation on that. And the idea is at 0, we're gonna have this like this approximate indicial equation. Because when p0, when you sub in pz is 0 here, when you sub in z is equal to 0 into the polynomials, you'll get some values, and we just approximate like this equation as z squared u double dash plus z p0 u dash plus q0 u. And in that case, the initial equation is this. From there, we guess the solution z to the r, which was the solution to the Euler-Cauchy, times by a power series. So for this ODE, determine the indicial equation and its roots to the ODE. To the ODE Frobenius method, which is applied to x0 equals to 0. Okay, so what we're saying here is we're going to do this as a power series around 0. The polynomials in this case, p of x is 1, and this is q of x. So we're going to sub in 0 into these and see what we get. We'll get, since p of x is 1, q of x is that, sub in 1, you get 1 and negative 1/9. So around 0, that's what this approximating Cauchy-Euler equation really is. It's around 0, the differential equation looks like this. And if we solve that using indicial equation, we will get these two roots. Okay. For part B, they taught us to work with a larger root to find the solution, or to write down the first few terms of the solution with Frobenius, with the Frobenius method. So we're going to let y be, remember it's x to the r sum of akx to the k. They just put this x to the r inside. Compute its derivatives. And then we substitute them into the left-hand side. Right, so we substitute them in directly. We're going to combine the first three terms because they all have the same power, x to the k plus r. And then the last term is just this term here. And so since this starts from x squared and then goes onwards, what we can do is we can write out the first two coefficients, and then we combine these two together into one sum. Okay, so yeah, as I said, if we just look at the first two terms, so the x to the r and the x to the r plus 1 terms, those only come from this first bit here. So sub in 0, sub in 1, you get these two terms. Now remember, r is 1/3, and we want this to be 0. So if we set this to be 0, then a0 can be anything, because this part's already 0. And then for the second one, if you sub in r as 1/3, you'll find that a1 has to be 0. Having removed that term, what we can do now is we can combine these two sums and have this actually start from 2. And you end up with this equation, or like this sum. And from here, since we want this to be 0 as well, we're going to set the coefficient of x to the k plus r to be 0. So yeah, eventually if you factor out x to the k plus r, you'll get this recursion. Remember a1 is 0, so all the odd terms are 0. So we just check the even terms. There should be an a0 here. If you check the even terms, first one will be a0, and then a2 will follow from this equation. a4 will also follow from this equation. Okay, and now here's some like special cases. Bessel function, Legendre equation. The Bessel function is the solution to the Bessel equation here, which is in Frobenius normal form, which I call f and f. If you just look at, if you find the indicial equation, so here p of z is 1. Wow. Yeah, so p of z is 1. Q of z is z squared minus nu squared. P of 0 is 1 and Q of 0 is minus nu squared. So the indicial equation is, if you calculate the indicial equation, it will end up being this, obviously with solutions plus minus nu. That means we want a solution of the form z to the r sum of ak z to the k, which they write as this. And then they assume that this parameter nu has a real part greater than or equal to 0. Don't worry too much about this. This is just, a lot of the things we do in this solution are just for convenience. And yeah, this is also for convenience. If we set a0 to be this, we get the Bessel function in a relatively nice form. And you'll just end up with this solution. Don't worry too much about this. This is more for the sake of, like, I guess, an application of the Frobenius normal form. Right, yeah, and The point of this normalization is the denominators will be like 1 plus nu, 1 plus nu, 2 plus nu. And if we keep going, then remember gamma function kind of works like the factorial. So if we have consecutive terms multiplied into there, then it will just simplify to the next gamma term. Okay. Yeah, so there's a lot of things here, but it's really not that important. If nu is not an integer, then you also get this solution from negative nu. But if nu is an integer, then you get this solution, and we replaced gamma into the factorial function because gamma and factorial are equivalent for integers. And then for the minus n case, you just get this expression using a simplification. 1 over gamma of z is 0 for negative values of z. Yeah, but again, don't worry too much about this. A Legendre equation looks a bit similar. Not singular as z is 0, so we have a Taylor series expansion as the solution. You find the recursion for it, and yeah, it's just very tedious. But don't worry too much about this. They're not gonna. I highly doubt they're gonna make you solve something like this in the actual exam. Cool. So that's the end of the first part. Unfortunately, it is just a bunch of equations and formulas. You just need to remember them and know how to do some basic integrals. Make sure you memorize, and you should be good. So now for dynamical systems, I'm going to hand off to Oscar. He will join you in just a second. Thanks for watching my part, and good luck for your exams.
state variables, yeah, it's just some natural variable xk. It could be like a state vector that we have x, y, z. It really, yeah, it really doesn't matter what it is. It's kind of arbitrary. But we say that this vector kind of describes the way some dynamical system, behaves at some given time t. So, yeah, a bit more terminology, definitions, all that kind of stuff. So we'll say that if we have a system of ODEs, right, as we've got one here, and we say that this is equal to f of x, some vector f of x, we say that it's autonomous if it doesn't actually depend on time t. So you'll notice that t here is not, there's no t. So it's not time dependent. So we say it's autonomous. And then I guess on the flip side, if it does depend on t, we say that it's non-autonomous. Yeah. So autonomous means no. I can't hear it. Is it not? Oh my god. Why is it not coming through? No, the audio's coming through. Yeah, audio's coming through. Okay. Yeah. Okay, sorry. We're just a bit of technical. Okay, so we should be good now. Again, this is just some definitions. We don't really need to know this. A bit more theory. We're saying that each solution x of the non-autonomous ODE corresponds to some solution y in an autonomous ODE. So really, this component here is just dx on dt, and this component here is just dt on dt, which is just trivially 1. So since this corresponds to some autonomous dynamical system, we're just going to be studying these. We're going to be looking at autonomous dynamical systems. That's really the main focus of this section of the seminar, or this, I guess, section of the course. So yeah, the question that we want to be asking. Wait, hold on. So yeah, the question that we want to be asking is, when does a solution x of t satisfying some initial condition, which is this x of 0 equals x naught, when does that exist? And on top of that, is this solution unique? And the answer to this is a thing called Lipschitz continuity. So yeah, so we're going to say that the solution to a dynamical system exists and it's unique if it satisfies this notion of Lipschitz continuity. So we're going to define what this means. So we say that some constant L, which is a real number, is a Lipschitz constant for some function on the interval AB if this inequality is satisfied. It's saying that effectively the distance between f of x and f of y is less than or equal to some constant times the distance in x and y. Okay, sorry, 1 sec. We're having more technical difficulties. It should be picking up my audio, and I'm really not sure why. It should just be hello. Maybe this might fix it. Hello? Yeah, just bear with me for a second. This might fix it. Hello? Oh, okay, I think that's a lot better now. Alright, just 1 second. Okay, are we getting sound? Alright. Is it working now? Are you getting sound? Okay, yep, sweet. Okay, now we are finally good to go. All right. So, yeah, back onto Lipschitz continuity. Okay, so Lipschitz continuity is this, it's a bit of a weird expression. You sort of look at it and you go, what does this actually mean? And I'll explain exactly what this means. So, it effectively is saying, in essence, that if we have some function like this, it's a bit jagged. What it's saying is that we can construct some kind of like cone, like this, such that no matter where we drag this cone along the function, no matter where this goes along the function is always contained inside this cone, inside this like Lipschitz cone. Because in essence what it's saying is that if we take some point, and I'll make this a bit small, this will be f of x, this will be f of y, then rearranging gives us this. And really the expression on the left-hand side is just like the gradient. So what it's saying is that the function effectively, it doesn't increase too quickly. There's always some kind of like cone that you can trap this entire thing in, like that, where the gradient or the function never increases more than the steepness of this cone. So what it means is that our solutions don't just blow up to infinity, and we don't get any of that weird stuff happening. So we're going to show that something is Lipschitz continuous, and we're going to look at some theorems first. The first theorem is going to be that if a function is Lipschitz continuous, it's uniformly continuous. Okay. So what's good about this statement is that we can take the contrapositive of this to get that if a function is not uniformly continuous, it's not Lipschitz continuous. So suppose they want to say, oh, show that this function is not Lipschitz continuous, we can just use this. We can take the contrapositive of this statement and happy days, we can prove that. Now the next one is if we want to prove something is Lipschitz continuous, this might help us. So we say if a function is continuously differentiable on a compact interval, then it's Lipschitz continuous on that interval. So just as a refresher, and this is, if you took Math2121, this will be familiar. So we say that this, some set, we say that some subset, some set is compact if its boundary is entirely contained in the set, and you can construct some epsilon ball centered at the origin such that it fully contains it. So in other words, you might have some like function here, omega, and you can construct some fixed epsilon ball like this that fully contains this. So this is fully contained in it, and we're saying that omega contains its entire boundary. So compact. So yeah, this is just a bit of, so if you've taken 2111, this will be familiar. If you've looked at a little bit of point set topology, this might also be familiar, but yeah, not super important. So we're going to look at an example. Is f of x equals e to the x Lipschitz on the reals? So without loss of generality, we're just going to suppose that x equals 0, right? Then, if f is Lipschitz on R, then there must exist some constant L such that this holds. And this just comes from the fact that f of x minus, so make this an x, is that. So we just say that, well, if x is 0, then e to the 0 is just 1. And then if y equals y, then e to the, or if x equals y, e to the x is e to the y. So we get this expression. Now, what we're saying is that this function on the left is bounded by a constant. But as we know, yeah, it fails to be Lipschitz because exponentials are dominating functions. So exponentials increase at a much faster rate than linear functions. Hence, our left-hand side is just going to, it's just going to blow up to infinity because the top goes to infinity significantly faster than the bottom. So there can't be any constant such that this is always less than that. You can't bound this function. So yeah, I guess the SparkNotes summary is just that function's unbounded. So it's not Lipschitz. All right. Happy days. So yeah, we can sort of extend Lipschitz continuity to vector fields. And I'm sort of just going to throw this in here because this is kind of cool to look at. But again, we're not going to be asked to prove Lipschitz continuity for vector fields. So you can sort of extend this definition by replacing your f of x with some vector field fx and some vector field f of y, and it's replacing x and y with vectors. And then this Lipschitz continuity thing holds. And it also holds if you have time-dependent vector fields, and it's just the same expression. So again, this is just showing that we can extend this beyond, R to R functions. So we move on to a definition. We have an n by n first-order system of ODEs given by dx on dt is some vector field f, or some vector function f of x and t. We say it's linear if we can write it in this form. We can say that it's some matrix times x plus some vector b, right? And we're going to say that A is an n by n matrix, because this is n by n. And b is just a vector valued function. Now, the system is autonomous when a and b are constant. Remember, we said that autonomous systems were the ones that we wanted to focus on. So, it gets quite nice when a and b are constant. So, yeah, we've got a stronger sense of existence in the linear case, stronger than this Lipschitz thing that we just looked at. So if a and b are continuous on some interval 0 to t, then the initial value problem, which is dx on dt, is a of t times x plus b of t with some initial condition, x naught equals, or x of 0 is x naught. It's got a unique solution on this interval. So we're going to try and build up from this. So again, it is nice when A is a constant matrix, and if B, our vector valued function, is 0, I mean, that's even nicer. We just get this really, really simple system here. Now, the general solution to this, right? We're going to assume that A is full rank. And then it follows that the solution is going to be some constant times e to the power of lambda t, or lambda it, where lambda I is just the ith eigenvalue of the matrix A, and vi is just the ith eigenvector of the system. So yeah, I guess the thing to take from this is if we want to solve the system here, we want to solve this thing here, we need to find eigenpairs. So, and now we're going to look at what happens when we raise e to the power of a matrix, which seems a bit, seems a bit stupid at first. Like, how can you raise e to the power of a matrix? But we can leverage the fact that e to the x can be written in the form, can be written in its infinite power series expression. So this is a Math 1b thing. So this is the Taylor series or Maclaurin series for e to the x. And since raising e to the power of a matrix doesn't make sense, but I mean, you can square matrices and you can cube them and you can raise them to the power of n. By diagonalizing, we do all this really cool stuff where we raise matrices to powers. We can just throw it into this e to the x expression and we get this right here. And this is the definition of e to the a. So, okay, why do we care about this? Well, this is nice because if we have this dynamical or this initial valued system here, dx on dt equals ax, with initial condition, I mean, this looks an awful lot like, you'd probably just guess, like you'd probably say, okay, well, dx on dt equals ax. This, would sort of lead you to thinking that, logically you just think, okay, this looks a bit like an exponential. This looks like the, exponential equation. So, okay, well, maybe we have e to the at times some constant. And then, well, at t equals 0, we have that x. So we got that x is equal to this thing. Should chuck that in there. Well, then at t equals 0, x equals x naught. So we have that x of 0 equals e to the 0 times c, which is just c, which is x naught. Therefore, x of t is going to be e to the at x naught. And that's the solution to our matrix exponential. Or that's the solution to the differential equation using matrix exponentials. So this is very useful. We're going to use this a lot. Okay, So we're going to quickly look at a problem, and I'm going to sort of provide a bit of insight as to, there's a result in here that we want to use, and I'm just going to show you what that result is real quick. Suppose that lambda and v is an eigenpair of some matrix A. Then we can say that AV equals lambda v. So if we apply A to both sides, this is equal to A squared v, and this is just lambda AV, which equals lambda squared v, because this is just lambda v. So in general, I mean, we can continue this. If you want to prove this by induction, by all means go for it, but we're just going to take this as a given. So if we raise, if v and lambda are an eigenpair for A, then A to the k times v is lambda to the k times v. So we're going to leverage this fact. So this is where we want to be looking. This here, we're going to write as, in its matrix exponential form. So we'll say this is the infinite sum of 1 on k factorial a to the kv. Notice this a to the kv is just going to be lambda to the kv, which was that result that we deduced just then. And then, I mean, it sort of follows trivially. We just throw this in, throw some brackets around it, that's e to the lambda, and we end up with e to the lambda v. And we'll put a big tick here. So yeah, that's a pretty cool property. So calculating, calculating e to the ta requires us to work out powers of matrices, which I don't know about you, I hate doing that. And we sort of want to avoid that like the plague. But there are certain situations where avoiding it is actually not a bad idea, because it's quite easy to do. So if A is a nilpotent matrix, so a nilpotent matrix is just a matrix that there exists some integer power that you raise it to, and it eventually becomes the zero matrix. So I mean, you could have like A is some non-zero matrix, A squared is a non-zero matrix, but then you do A cubed and you end up with the zero matrix. So that means that it will be nilpotent for, like, for instance, n equals 3. So A cubed is 0. So if it's nilpotent, we can find that n value for which we get the zero matrix. And that means that every single subsequent matrix power is going to be 0. So we can partition our sum into the bits that are not 0 and the bits that equal 0. So then this whole thing here just kind of disappears, and we're just left with this. And that's our matrix sum. So yeah, that's quite nice. I mean, you can probably intuitively see why that's nice. So another case where we can calculate matrix exponentials is if our matrix A is diagonalizable. So we don't even have to do this we can entirely just skip getting A to the K. We can skip all this annoying stuff, right? And we're going to look at diagonalization in the next part, next slide. And another case is where you can write A as two commuting matrices, as the sum of two commuting matrices. So if I say A equals B plus C, where BC equals CB, it doesn't matter what way you multiply them, you get the same thing every time, then you can exponentiate both sides and you get e to the A equals e to the B plus C. So then e to the A is e to the B times e to the C. And since we have that nice commuting property, we can, it might be a lot easier to find e to the B and e to the C. If they're, those might be nilpotent matrices, and we can easily find that. So we only use this when we can decompose it into the product or the sum of two simpler matrices. So this would have been in the past papers. So there was a few questions on that. But here's the real kicker. This is what we want to look at. Diagonalizing a matrix. This is the cool stuff. So again, this is just a bit of revision from Math 1B. So if you've got an n by n complex matrix A, we say it's diagonal or diagonalizable if there exists a non-singular n by n matrix Q such that Q inverse A Q is diagonal. Okay, so here comes a theorem. If we've got some n by n complex matrix A, and we're going to say that it's diagonalizable But the catch is, if and only if there exists an eigenbasis for Cn. And moreover, we call this, we say that this matrix lambda, or we're going to define this lambda matrix, right? And it's going to be equal to this. We say it's Q inverse AQ, with the Q matrix being the matrix consisting of our eigenvectors. So this is our eigenvector matrix, and lambda is our eigenvalue matrix. So it'll be eigenvalues along the diagonal, zeros everywhere else. So again, this is just revision from Math 1B. You would have seen this before, diagonalizing matrices. So you can just take a matrix A and you can find its eigenvalues, find its eigenvectors, and take the eigenvalue matrix, make it diagonal, and sandwich it between its two eigenvector matrices. And one of them is going to be an inverse matrix, of course. So yeah, this is just revision. And the really important thing that you have to be careful of, unless you're going to get, if you're not careful of this, you're going to get the whole thing wrong. We say that lambda I is the eigenvalue that corresponds to lambda V. So if I've got V1 as the first eigenvector in the matrix here, then lambda 1 has to be the first eigenvalue, and these have to form an eigenpair. These have to be corresponding eigenvector eigenvalues, or else it'll just be wrong. So you just got to be careful with how you put your terms in there, but it's nothing too bad. So matrix powers. So the reason why we actually care about diagonalizing matrices is because we get this really nice property. If you want to raise A to some absurdly large power, whatever you want K to be, then if we said, okay, well, A is going to be Q lambda Q inverse, right? If we do A to the K, it's just going to be Q lambda Q inverse, Q lambda Q inverse, dot, 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 Q lambda Q inverse, K times. And the really nice thing is you have a Q inverse here and a Q here. Bang. They cancel, they give you the identity matrix, which we can just sort of omit because the identity matrix is sort of analogous to multiplying by 1. Then we're going to have a Q and a Q inverse in here, identity. Q inverse, Q here, identity. So really we just get that A to the K equals Q lambda times dot, dot, dot times lambda Q inverse. And this here is going to be K times. So we get Q lambda to the K Q inverse. And the reason why that's really good is because when you raise a diagonal matrix to a power, you just raise the diagonal terms to that power. So as you can see there, really nice. Okay, so now the exponential of a diagonalizable matrix. So it gets even better. Diagonal matrices are very nice. So if A has this diagonalization, Q lambda Q inverse, then we say that e to the A is just Q, and then instead of lambda, it's just e to the lambda, right? Very nice. E to lambda, and then we throw the Q inverse on the end. And then it's even better because when you raise a diagonal matrix we raise e to the power of a diagonal matrix, you just take all of the diagonal terms and you make it e to the power of that term. So now we get e to the power of all of the eigenvalues along the diagonal. Okay, and now oftentimes we want to find what e to the ta is, since that's the solution to our differential equations. So it's just going to be q e to the t lambda. So this is supposed to be a lambda here. Let me just change this. That is a capital lambda. E to the t lambda is q e to the t lambda q inverse because it's diagonalizable. And then it follows from this that we just throw a t in front of all of the lambdas, and sick. We've got this really cool exponential matrix. And yeah, so the real upshot of this is if you can diagonalize, you can exponentiate matrices. If you can exponentiate matrices, you can solve differential equations. Now, what if you can't diagonalize it? Uh-oh. We run into a roadblock here. Okay. But luckily for us, we have this method called Putz's algorithm. So suppose that we've got some defective matrix, meaning it's not diagonalizable. Like for instance, we might have missing eigenvectors, we might have double ups in eigenvalues, all this kind of stuff that just gets in our way, and we can't diagonalize it. Okay. Well, since the matrix is non-diagonalizable, we've got to resort to this new method. So let lambda j from 1 to n be a collection of n not necessarily distinct eigenvalues for a given matrix. So we might have double ups in eigenvalues. Then we say that e to the at is this sum from k equals 0 to n minus 1 of some polynomial p of k plus 1t times some matrix mk. So we've got to start defining what everything is. Okay, we've got a lot of things here and not a lot of definitions. So we're going to put some definitions in. We'll say M0 is I, identity matrix, and MK is going to be the product of A minus lambda Ji. Okay. This looks a little bit like, it's a little bit like when you're solving for eigenvalues and you get like your characteristic polynomial. It looks a little bit similar to that. So we don't know what P is yet, so we're going to define what P is. So there's a little bit more. We define this vector valued function P, which is consisting of n component functions, P1 up to Pn. We say that P dash satisfies this equation. So P dash T is this big lower triangular matrix consisting of eigenvalues on the diagonal, and we have ones below each eigenvalue. So this looks a little bit like the Jordan canonical form. However, we've got ones below the diagonals. So yeah, interesting coincidence. I'm sure there's something there. I'm just not 100% sure what that is, but we don't really have to worry about that. So we take this matrix, we multiply it by P of T, and that's how we get P dash T. And we say that the initial condition P0 is this vector with zeros everywhere except for the first entry, which is 1. Okay, so this looks quite horrific. This looks horrible. I don't like this expression, but I like this expression. So we only have to know Putz's algorithm for n equals 2 and n equals 3. We're not going to be asked to compute anything beyond this. So this is what's been said in the lectures, which is very nice, because it is a bit of an ordeal. But we say that e to the at for n equals 2 is just P1 of T times the identity matrix plus P2 of T times A minus lambda I. And in this case, we're going to have double ups in eigenvalues. So the eigenvalue 1 and eigenvalue 2 are going to be the same. So n equals 3 case, we just take this exact same expression here, and we just throw that here. And now we just have this additional term. P3 of T is A minus lambda 1i times A minus lambda 2i. And yeah, that'll be the additional new matrix thingy that we get there. So yeah, we only need to know these two cases. I'm almost inclined to say that if you're going to memorize any of these, memorize n equals 2, because n equals 3 rarely pops up, and yeah, the n equals 2 case is far more common. So let's actually look at an example of Putz's algorithm. So suppose a matrix A is given by this. Using Putz's algorithm, we want to find e to the at and hence obtain the general solution to the homogeneous vector equation x dash is ax. Okay, find eigenpairs. So by inspection, our characteristic polynomial, you just kind of look at this by inspection, 3 minus lambda on the diagonal, take the determinant, the opposite diagonal just goes to 0 because you've got a 0 term there. So our characteristic polynomial is just 3 minus lambda squared equals 0. So we've got lambda 1 equals lambda 2 equals 3. Okay, this is classic Putz's algorithm shenanigans going on. So if we say that, lambda 1 is lambda 2, A is defective. Okay, so we have to use Putz's algorithm. Let's define P of T. So P of T, remember, was our diagonal matrix with the eigenvalues along the diagonal and the ones below each eigenvalue. So the only spot that we can put a 1 below an eigenvalue is in this left column. It's this spot here. So we put 1 there. And then we sub in our values. So lambdas, they're both equal to 3. So we get 3, 0, 1, 3. Very nice. And yeah, we can say that P of T is this function P1, P2. So by doing the matrix multiplication here, we're going to end up, say, for instance, and I'll just show you this really quickly. Expanding this out and saying that this is P dash, we get that like P dash 1 equals this times this, 3P1 plus 0. So that's how you get the first one, and then you just do the matrix multiplication on the bottom row, and you end up with this second differential equation here. And yeah, this yields the solutions P1 of T equals e to the 3t, and notice that this is the exact solution. There's no constant at the front, and that is thanks to this vector here. So we sub in the initial conditions, we get that. P2 of T, we're just solving this differential equation here. So I hope that you trust me in that this is equal to T e to the 3t. You can sort of do this by inspection. You do enough of these questions and it's always the same thing every single time. So yeah, we get P1 and P2 is that. So thus by Putz's algorithm, we just say it's P1 times I, okay, plus P2 times A minus 3i. We do the matrix multiplication, and there we go. We got this. And that is e to the at by Putz's algorithm. Finally, the solution to the homogeneous vector equation is going to be some constant times this, because we're not given the initial condition. Remember, this c here has to be x naught if we have a particular solution, but we don't. So, and yeah, because here there's no initial condition given to us. So we just go there and we say, do this matrix multiplication, and we end up with this is our solution. Notice that this here is an eigendirection. So if you draw the phase portrait of this, you're going to get a straight line. And then this here has a t in it, so it's not an eigendirection. Yep. And then c is some arbitrary constant vector. Okay. So sort of what we've done from this is we've said, okay, e to the at times c is going to be, it's going to encode every solution to our differential equation. So we're going to call this here something called a fundamental matrix, which is this here. We say that, suppose that capital phi is some fundamental matrix for the vector equation x dash equals ax. Then if it's a fundamental matrix, it means that every single solution is of the form phi c for some constant vector c. So this will encompass every single solution to our equation. And another property of this is that if it's a fundamental matrix for the system, then the solution is going to be phi of t times phi inverse evaluated at 0 times x naught. And that there is a solution. So you might be thinking, okay, how do we calculate a fundamental matrix? What does that actually look like? Well, it's very simple. Suppose that we have some ODE with general solution x equals this. Then we can express the solution like just throwing these into the vectors, like taking these exponential things and throwing them into the components. And then we add the whole thing together to get this matrix here. Okay, recognize that we can just turn this into the product of two matrices. We can say it's the product of all the exponential terms in here, and we've got some constant matrix here. Because when you do the matrix multiplication, you're going to end up with the thing on the left here. So we let this purple matrix, the thing that I've highlighted in purple, we're going to let this be phi, and we're going to let this be some constant c. So we conclude that phi is equal to this. It's equal to this matrix here. So if you have the general solution, just discard the C1 and the C2, and then you just add it together, and that's a fundamental matrix for the system. And then calculating the inverse of it, you just divide by the determinant, take the adjunct matrix, and well, that just means you switch the diagonals around and make all the other terms negative, and there you go. Sub in t equals 0, and yeah. Now here's it's a bit of a tragic formula. It's a lot. But this is unfortunately one that you just have to remember. It's called variation of constants. So you should be familiar with this. This was on every single practice exam for test 2, and this was on the actual test 2 as well. So just as a refresher, if x dash t equals ax of t plus some vector valued function f of t, not necessarily constant, where the initial condition is x naught, then we say that x of t is e to the at x naught plus e to the at times the integral from 0 to t, and inside the integral we have e to the minus as times f of s ds. Okay, that's a mouthful right there, but to get e to the minus as, if we have e to the at, we just replace every t with a minus s. So that's all we're doing, nothing too fancy going on there. So we're going to really quickly look at an example because good to see this in practice. So if x of t is ax plus some, scary vector valued function here, f, with the initial condition 1, 1. So given that the matrix exponential is this, we want to find the unique solution. Okay, so we're just going to take this formula like that. And I won't necessarily go through all of this because it's just a bunch of matrix multiplication, which is not very interesting. But you just sub it in, e to the at, we had that, times x naught. The real important part here is that e to the minus as becomes this. So we just replace the t here with a minus s. Replace the t and the t here with minus s's. We replace the t here with a minus s, and we end up with this thing here. And yeah, you just compute all this big matrix multiplication, you go through, and Bob's your uncle, you get the answer. There we go. So that's variation of constants. It's just a lot of algebra, but it's nothing too crazy. So if you remember the solution, which is this formula here, you're pretty much set. It's just going to be a lot of matrix multiplication. So now we move on to, we're going to start looking at differential equations. We're going to look at the behavior of these differential equations and, you know, some analytical methods to sort of suss out what's happening without necessarily, you know, finding like exact solutions. We want to look at the behavior of these things. So we're going to say, we're going to define what equilibrium points are. So we say that A, some point in Rn, is an equilibrium point for a dynamical system, and it's determined by the vector field F if f of A is 0. So suppose that we have some equilibrium A in the system. Then if we have this initial valued system, f of x equals, dx on dt is f of x, and we start at this point, A. Oh, okay. So we're starting on the equilibrium point. Right. We know it's an equilibrium point, so that means that f of A equals 0. So that means that the derivative is going to be 0. That means our function does not change, ever. So our solution is just this. It stays on that equilibrium. So x of t is always equal to A. So basically, if you start on the equilibrium, you stay on the equilibrium, right? Nothing too fancy. So stable equilibrium. So we're going to look at some epsilon delta definitions, which you're not going to be asked to replicate this, but this is just, we're building up some more theoretical framework. So we're going to say that an equilibrium point A is stable if for every epsilon greater than 0, there's a delta greater than 0 such that whenever the distance between our starting point and the equilibrium point is less than delta, the solution to this dynamical system here satisfies the fact that the position in the system at any time, or the distance between the position at any time and the equilibrium point is less than epsilon. So I guess in plain simple terms, if your solution starts close to the equilibrium, you stay close to the equilibrium. Yeah. So again, we don't really need to know this super in depth. This one I feel like is a bit more important. Asymptotic stability. This is the cool one. So this is an even stronger form of stability. So this is when we look at subsets of Rn. So definition, let D be an open subset in Rn that contains an equilibrium point A. We say that A is asymptotically stable in D if A is stable, and whenever x naught is in D, the solution to this dynamical system approaches A as T approaches infinity. And we call that open subset in Rn, we call that the domain of attraction. So I'm going to draw a quick little diagram because I think it's pretty cool. So if we've got this space, suppose I call this Rn. I'm going to draw some open set in here. And I'm going to label a point in here and say that this is A. Actually, I'm not going to put the vector thing on there. We're just going to say this is point A. Now, if we take any point x naught, starting in this region D, as time progresses, this point is going to tend towards A. Or if x naught is here, it might tend towards A. X naught's here, it'll tend towards A. So it doesn't matter where you start in this region, it always floats towards A as t goes to infinity. So given enough time, it will approach A. But if you pick a point not inside this set, like out here, it's not in the domain of attraction, so it might just fly off this way. Or you might have a point that's here, that goes off and does whatever. And it's not pulled towards the equilibrium because it's not inside the domain of attraction. So when we look at phase portraits, this notion is going to become very important. And we're going to see that for our phase portraits, oftentimes our domain of attraction is Rn, or in most cases it'll be R2. So here's just a bit of extra theory stuff. If we have a dynamical or linear system, dx on dt is ax plus b, initial condition x naught, where a is non-singular, meaning we've got an inverse, then the unique equilibrium point is given by a equals a negative a inverse b. And that's yeah, we're simply just saying that ax plus b equals 0. So then we move the a over to the other side, or we move the b over to the other side, get negative, multiply both sides by a inverse, yada, yada, yada. We end up with that. So this isn't too important. And it satisfies this. So yeah, we've got this. Again, this isn't super important. This is just an interesting fact that we're going to point out. So this is important though. This is what we care about. So theorem 14. So we're going to consider this previous linear constant coefficient system. So this system that we have here. We consider this and we want to talk about the stability of the system. We'll say, well, if it has a set of eigenvalues, like if our matrix A has a set of eigenvalues lambda 1, lambda 2, yada, 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 lambda n, then the equilibrium point is stable if and only if the real component of all the eigenvalues are less than or equal to 0 for every single eigenvalue. So it doesn't matter what eigenvalue you pick out of there, if the real component for any arbitrary eigenvalue is less than or equal to 0, then it's stable. Okay. And then we have asymptotic stability. So if it satisfies the inequality, but if it satisfies like the real component is less than 0, but doesn't satisfy this equal to thing, then we say that it's asymptotically stable and the domain of attraction is going to be Rn. So if neither of these are satisfied, we have unstable points. We have an unstable equilibrium. I guess we just call this system unstable. So given this system, dx on dt is ax with a non-singular, the general solution is going to be one of two things. So we consider the case where the eigenvalues are real and we have linearly independent eigenvectors. Then, as we saw before, we just write it as, this comes from the definition. So that just comes from that definition of the solution to a system. And then if lambda 1 equals lambda 2, then, we can just absorb these two into each other. Yeah, and we just get C1 e to the lambda 1, t times V1. Now, if the eigenvalues are complex conjugates, then we get this strange business going on where we separate the real and imaginary components. So we're going to have a look at what different trajectories we get from these types of systems. So again, we're gonna say in these cases that the equilibrium point is a equals 0. It'll be the origin. So we're gonna look at some examples. Stable nodes. These ones are nice. So if both of our eigenvalues are less than 0, okay, then we know it's going to be asymptotically stable because it's less than 0. So what we want to do is we want to draw lines that span the eigenvectors. So in this case, our eigenvectors here might look like, it might be like this line here, and then like this line here. A bit hard to see, but I'll do it in like another color and I'll make it really small. So do this, and it might be like this. So those might be our two eigenvectors, and we draw the spans of these eigenvectors. And you notice how there's directional arrows on there. There's arrows pointing in some direction. There's one here, arrows here, right? If those arrows are pointing inwards towards the origin, that arises from the fact that our eigenvalues are negative. So, and any particle that, if you think of like a particle entering this like getting shot into R2, with these two eigen directions, which are the spans of the eigenvectors, pulling it in towards the origin, you can imagine, you think of it like a force field, right? This particle gets shot in, and it starts getting pulled by the eigenvectors towards the origin. So it ends up here, like that. And you can sort of, just deduce this from the fact that we have this. If you take the limit as t goes to infinity, ae to the minus 3t goes to 0, be to the minus t also goes to 0. So as t approaches infinity, our x thing approaches 0. So it approaches our equilibrium, so it's an asymptotically stable equilibrium, which, is again what we saw here. So unstable nodes, if they're both positive, we draw the same diagram. We draw our spans of our eigenvectors. And if it's positive, the directions are going to be pointing outwards. So you think of like, again, a particle getting shot into here, into R2, it just gets flung away from it, right? It's trying to push the particle as far away from these eigendirections as possible. So it spits everything out. And it'll sometimes be these weird, like funky trajectories that are, curved. You get all these weird curves, and that's because certain directions are pulling more than other directions. So this has a 2t here, this only has a t here. So the 2t is going to push it away much with more, I guess, force, not necessarily in a like physics sense, but it pushes it away with more force than the e to the t. So yeah, that's why you get these non-linear lines. So yeah, unstable stars. Okay, let's suppose that lambda 1 equals lambda 2. So all non-zero vectors are eigenvectors. Okay, so that means that any trajectory lies along an eigendirection. So if our eigenvalue is negative, it gets sucked in towards the origin because the eigendirections are pulling it inwards. If it's positive, then it repels everything from the origin. So again, I guess a little math 2121 interlude. This is a bit like sources and sinks in vector fields. This would be lambda less than 0. This is lambda greater than 0. Yeah, this is just analogous to sources and sinks in a vector field. So in this case, we see that all of the directions are going outwards. So we can say, well, lambda is going to be greater than 0. So yeah, we either get inward attraction or outward repulsion. That's depending on whether it's positive or negative. So this is probably the most common example that we're going to look at, and it's unstable saddle nodes. So if one of our eigenvalues is negative and one of our eigenvalues is positive, our solution is going to end up looking like this. We're going to have a minus t here, and we're going to have like a positive t here. So that means that these two eigendirections are sort of fighting against each other. And one eigendirection wants to pull a particle in, and one eigendirection wants to repel the particle away. So we get some solutions like, pick this color, this might be a bit easier to see. So like a particle might come in and get pulled toward, like if this is going inwards, and then this direction is going outwards. It gets pulled in, and then it starts to feel the presence of this direction along here. And that presence is going to push it away from the origin. So hence we get these subtle lines that look like this. It'll be like that. So yeah, and I mean you can sort of again look at the solution, look at how the t's vary as t gets really large, and yeah, it's sort of this indeterminate thing. Yeah, I mean not indeterminate. One of these terms is going to go to 0, one of these is going to go to infinity. So the only case where you might end up at the origin is when b, this coefficient here, is 0. If this coefficient b is 0, then what that implies is that we're lying on an eigendirection. So our trajectory begins on one of the eigenvectors, And if it's the eigenvector that's pulling it in towards the origin, that means that that'll mean that b is 0. So that term that would blow up to infinity is contributing nothing. Hence, we can safely just float towards the origin as t gets very large. So, centers, yeah. So this is when our eigenvalues get imaginary and we get some really weird stuff going on. So if it's purely imaginary, we get these trajectories that form like elliptical orbits around our equilibrium point. So this diagram here is what it looks like. And it's going to be elliptical because we can decompose, since we always have to have an e to the lambda t. If it's purely imaginary, we're going to get like e to the I something. And we can decompose it using Euler's exponential form into cos t plus I sine t. And then, so you're going to get this weird elliptical shape going on. And then if you want to determine what direction it's going in, just evaluate the derivative at some point and it'll tell you what direction it's moving in. So yeah, this isn't as large a focus. This is more so just here are some more applications of it. We're going to be looking at these a lot more though. So these, you don't need to put as nearly as big as an emphasis on it. So now if it's not just purely imaginary, but we have a real and imaginary component, so they occur in complex conjugates. So we'll say that we have alpha plus I beta is our eigenvalue. And then lambda 2 is going to occur in a complex conjugate, so it's just going to be alpha minus I beta. So if our real component is negative, we spiral inwards towards the center. If it's positive, we spiral outwards. It's going to be pushing it away, repelling it. And then again, you can just evaluate the derivative to see what direction it's going in. So let's have a look at an example. Here's a system of differential equations. Okay, we want to find eigenpairs. I mean, yeah, we're gonna look at what it's asking. So A, find the general solution. Okay, sweet, eigenpairs. B, determine the nature and stability of the equilibrium point. Okay, so we want to work out which one of these things is it? Is it going to be star? Is it going to be an unstable node? Is it going to be a saddle? Is it going to be a center? Is it going to be a stable foci? Is it going to be, so many things that we could pick from. But we want to find the general solution, so we look for the eigenpairs. So we write this in matrix form. And the way that we've done this is we've just ripped the coefficients from here. Here, 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 and here. We just take those coefficients and throw them into a matrix. Like that. And now we just look for the eigenvalues of the matrix. So we can use the trace determinant method. So this is a nice little linear algebra fact. The trace of a matrix is the sum of the eigenvalues, and the determinant of the matrix is the product of the eigenvalues. So yeah, this sort of trivializes a lot of, we can avoid the characteristic polynomial entirely, and I guess just like by inspection you can sort of do this. You just go, okay, lambda 1 plus lambda 2 is going to be negative 1, and then if I multiply the two things together I get negative 12. Okay, so maybe I'm looking at negative 4 and 3, which is exactly what we're looking at. So we'll say, okay, eigenvalues, lambda 1 is 3, lambda 2 is negative 4. Sweet. Throw this into the eigenvector equation, and we just solve for eigenvectors as follows. So this is just standard procedure, nothing fancy going on. So we get the first eigenvector. And now I leave this to you to work out. If you throw in, instead of negative 3, you put a positive 4 in there, we end up getting the second eigenvector is 1, 1. So by same methods, nothing crazy going on. Now our general solution is this. Okay. So since one of our eigenvalues is negative, one of our eigenvalues is positive, the equilibrium point 0, 0 is an unstable saddle. It's a saddle node, or saddle point, sorry. Unstable saddle point. So as a bonus, we're going to draw a phase portrait. And we're going to look at the associated eigendirections, and we're going to draw in some representative solution trajectories to sort of understand what's going on. So, phase portrait. Let's get this going. So we'll do this. X and Y directions. First eigenvector we're going to draw in is 1, 1. That's a pretty easy one to draw in. And I'll do them in red. Oops. It's going a bit squiggly. I don't know why it does that. But so this is our first eigendirection, and the associated eigenvalue is lambda equals negative 4. So it's negative. It's pulling inwards. And I might actually just get rid of the arrows on the ends. So this is pulling inwards because the eigenvalue is negative. Now, the next one is negative 6, 1. So let's draw this eigenvector in. This is going to look a little bit like something like this. And we have that lambda equals 3. So this is repelling. So we get a bit of repulsion going on. Now, a representative solution trajectory to this might be something like something comes in, or it's getting pulled in towards negative 4 and it wants to go towards the equilibrium, but then lambda equals 3 comes in and it pushes it away. We might have something that comes in like this. Or something like that. These are just some solution trajectories. It'll look a bit like that. And then this is we'll also draw the trajectory. If we lie along this eigenvector, we go straight to the origin. And that is only if we are on the eigendirection of the eigenvector with the negative eigenvalue. Okay, so we're going to briefly touch on first integrals, just because this was actually there was a problem on this in the problem set, the tutorial problem set, but yeah, we're not really going to be, this is not going to be heavily assessed at all. So, but again, maybe they might throw something in there. This was in the tutorial set, so just being mindful of that. So when we get nonlinear problems, they're a little bit harder to solve and we have to get a bit more creative. But we've got a method called first integrals. Okay, so if we've got a function g, which is r into r, we claim that this is a first integral for the ODE if g is constant for every solution. So geometrically, we can say that it's a first integral if the gradient of g is perpendicular to f for all x. So just a reminder, the gradient or nabla of g is just the vector consisting of the partial derivatives. So we just take the partial derivative of the function with respect to all variables. This is obviously a three-dimensional case. This is if g is r3 to r. But yeah, so we can turn this into a vector by using this vector operator nabla. So let's look at a very quick example. We're going to say, okay, find the first integral of this system. All right, we've got what f is. We've got this x minus xy, xy minus xy minus y. Okay, so and then we want to do a bit of a sanity check to make sure that we've done it right by showing it's perpendicular. And showing it's perpendicular is the same as doing the dot product and showing it's 0. Okay, here's a really helpful hint. We want to find dy dx first. Okay, well, if we notice that this here is the derivative of x, this here is technically like our this is really our dx on dt, and this is really our dy on dt. And I'll put this in quotations because it's not necessarily like x and y, because this is in terms of x and y, but to find dy dx is equal to dy by the chain rule. Okay. So dy on dx equals dy on dt times dt on dx. This is just a chain rule. And if you don't believe me, just cancel these. Boom. We're right back to where we started. So by the chain rule, we leverage the fact that this here is dx on dt, and this here is dy on dt. So dy on dt gives us this, and then dt on dx is just 1 on dx on dt. So it's just going to be 1 on this, which is where we get this from. Okay, and we've claimed that this here is equal to dy on dx. And this is a separable ODE. So we can separate it like that. And now we're just going to integrate both sides with respect to their respective variables. So 1 on y minus 1 will integrate with respect to y, and 1 minus 1 on x will integrate with respect to x. So we'll slap some integrals on here. So the left-hand side gives us ln y minus y, and I'll just show this so you can see it. And then the right-hand side gives us x minus ln x plus a constant. Okay. We want our thing to equal a constant. We want g to be constant for everything. So we move everything to the left side, except for the constant. So we throw the ln x over to the other side, and we throw the x over here. So ln x, or ln y plus ln x becomes ln x plus, or ln xy. And then minus y minus x just becomes minus, and then we'll throw x plus y in brackets. And we'll say that it's a constant. Okay, this is a bit yucky, but we can raise both sides to the power of e. And I mean, e to the c is just going to be a constant. And then the left side simplifies really nicely to xy e to the minus x minus y is equal to some constant c. Okay, so we've got, for every single xy, we found a function that's constant. Okay. So we're going to claim that our first integral for the system is that. So that's how we find it. It's just a nice systematic process. Find dy dx, chain rule it, boom. Bit of simplifying, equate it to a constant. That's what we get. So as a sanity check, we want to show that if this is indeed a first integral, it'll satisfy this. So we evaluate nabla of G. And yeah, so this is obviously, it's a bit of working. Taking partial derivatives of this with respect to x and y is a little bit annoying. It's a bit of product rule stuff going on there. But if you trust that this is correct, yeah, we evaluate this dot product, and it's really nice because we keep the e to the minus x minus y out, and this is just going to be, we have this xy times x minus 1 times y minus 1, and we have an xy times x minus 1 times y minus 1 here. But we have a negative here. So this whole thing inside here goes to 0. So we arrive at the solution that these are perpendicular at 0. G is therefore the first integral of this system. So yeah, that's how we check our solution is right. And yeah, that about wraps up all of dynamical systems. So yeah, the real key takeaways from that is the phase portrait stuff and solving, finding the eigenpairs, and then knowing what each eigenvalues represent. So yeah, that's really the crux of this topic. We're just solving systems like that. And oftentimes we're going to be asked to get, phase portraits and determine the nature of the stability, all that kind of stuff. So if you can get your head around that, you're pretty much set. So that's what a lot of the past exams focus on. That's what a lot of the test 2 stuff was focusing on. So yeah, hopefully that makes a bit of sense. And yeah, good luck with your studies. Hope it all goes well. But yeah, we've got part 2 of the differential equations seminar will be taking place tomorrow at 1 p.m. to 3 p.m. So we're going to be looking at boundary value problems in 1D, and then we're going to look at all the generalized Fourier series stuff. But yeah, feel free to tune in for that. But yeah, that I guess brings today's seminar to a close.